Okay. Good afternoon. Can you hear me? Good afternoon. On behalf of the Southampton Theory, Astrophysics and Gravity Research Center, it's my pleasure to welcome you all here at the University of Southampton. I'd like to extend a special welcome to the students who are visiting us from local schools and our distinguished guests from the university and from the faculties who are supporting our research center. My name is Felix Hale. I am the director of the STAG Research Center, which has existed now for over a decade. And I would like to take a moment to thank Professor Matt Middleton. He has been running this research center for the last 3 years very successfully. Thank you for that. Now, let me tell you a little bit. Yeah. Let me tell you a little bit more about what it is we do. So STAG consists of scientists who are interested in some of the most fundamental questions about nature and the universe. And that is not a small task. So it really requires ideas and input from many different directions. For example, I work on mathematical physics, on theoretical ideas about bringing together gravity and quantum physics. So I belong to the theory part of STAG. Then we have astrophysics. My colleagues in astrophysics explore the actual universe out there, galaxies, black holes. And finally, we have scientists working specifically on gravitational physics. For example, gravitational waves and neutron stars. So the mission of STAG is indeed to bring together researchers from different areas of physics and mathematics, to learn from each other, to explore, emphasize, and strengthen our common interests, and to help making Southampton a center of excellence in these interconnected and active fields of research. Now, apart from the research that excites us, we also see it as our mission to raise public awareness of science. We do this through a number of different activities and events and channels. I encourage you to sign up for our mailing list if you'd like to be kept in the loop. Today is our biggest event of the year, our annual public lecture, for which we have always been very fortunate to have highly distinguished scientists to give us an overview of their field of research. Today is no different. We will hear a first-hand account of some of the most fascinating developments in the study of black holes. But before we get to that, another thing we do is every year we award publication prizes to our own PhD students from our research groups who have done outstanding work during the last year. So we will have a very small ceremony now to celebrate these achievements. To award the prizes to our students, it's my pleasure to invite Professor Pauline Leonard to join me, who is the Associate Dean Research and Enterprise in the Faculty of Social Sciences. Pauline, please.
Thank you. Thank you very much. And it's my delightful pleasure to announce 4 publication prizes this afternoon. The first STAG Publication Prize in Astrophysics is awarded to Matthew Stepney. Is he here? Shall I read first? Matthew has won this prize for his paper, A Big Red Dot, Scattered Light, Host Galaxy Signatures, and Multi-Phase Gas Flows in a Heavily Reddened Quasar at Cosmic Noon. Great title. Matthew is the lead author on this study of merging galaxies in the very distant universe, which are heavily obscured by interstellar dust. Such dust-obscured galaxies and their supermassive black holes are thought to play an important yet poorly understood role in the evolution of massive gas galaxies. Matthew has analysed complex data from the state-of-the-art European Southern Observatory's Very Large Telescope to produce the first detailed spectroscopic analysis of such a galaxy merger. The results have implications for our understanding of how black holes grow. So very well done, Matthew. Well done. Well done. The STAG Publication Prize in Gravitational Physics goes to Yashawi Ganwa. Is Yashawi here? Congratulations, Yashawi, for her paper, Applying the Starquake Model to Study the Formation of Elastic Mountains on Spinning Neutron Stars. Another great title. The paper concerns gravitational wave emission from neutron stars, a topic whose importance was recognized with the Nobel Prize in 2017. While the gravitational waves that have been measured so far all originated from binary neutron star systems, Yashawi's theoretical work looks ahead towards detecting gravitational waves emitted by individual neutron stars. In her work, she studies how fast-spinning neutron stars can develop an asymmetric shape that leads to the emission of gravitational waves. This work helps gravitational wave astronomers to decide which stars to target and what signals to look for. So huge congratulations. And the STAG Publication Prize in High Energy Physics is awarded jointly to Ernesto Bianchi and Savas Pitsanikos. Ernesto receives the prize for his paper Bulk Renormalization and the ADS/CFT correspondence. Ernesto's paper solves an important theoretical problem. It establishes some of the basic and most well-known rules of quantum field theory for universes with negative curvature. Even though such universes differ from our own, they are of greater importance in string theory and quantum gravity. Ernesto developed a completely new and general methodology to perform some of the most subtle quantum field theory calculations in these space times. So very well done. Finally, but not least, Savas receives the prize for his paper, Chiral Crossover versus Chiral Density Wave. Savas studied an exotic state of matter that can be found in neutron stars, dense nuclear matter. Savas solved some long-standing theoretical problems that allowed him for the first time to gain a deep understanding of the physics of chiral density waves in such stars. This work opens the door to a deeper understanding of a whole class of models that are being used to describe extremely dense matter. So very well done.
Thank you very much, Professor Leonard. We will now get to the main event. Let me only say briefly, for those joining us on Zoom, if you have questions, please use the Q&A functionality, and we will read out your questions in the end. We are honored to have the university's Senior Vice President Academic, Professor Philip Wright, who will introduce this year's STAG lecturer.
Thanks very much. It's been my pleasure over the last few years to come to the STAG lecture, and I've found them very, very interesting. So my background's chemical engineering. I can't profess to know an awful lot about physics. I did study some a long time ago, and I did actually specialize in astronomy when I graduated high school. So I do know a little bit about astrophysics. So I'm very interested to hear the talk this afternoon. And it is my great pleasure to introduce Professor Sera Markoff, who will be giving the STAG public lecture this afternoon. as you can see on the topic there, it looks to be a very, very interesting topic, and today's lecture will be about this most recent, one of the most exciting recent experiments in astronomy, the Event Horizon Telescope, and how that's been used. And we'll learn very much about the first images of black holes, which many of you may have seen on the front page of your favourite newspaper, on various websites and social media, etc., in April 2019. I think it's fair to say these images are a wonderful example of international collaboration involving hundreds of scientists around the world who collectively made it possible to observe the unobservable. And for those of you that work in science and in various areas, I think collaboration and working with people is actually the most exciting part, and actually sometimes that can even trump the work itself. So I think working with people is a very exciting part of progress today, and I think that this is a very, very key example of that, and I'm sure we'll hear much more about this. Nonetheless, I think with this important scientific effort, it's fair to say that Sera Markoff has been a leading figure in this research, and I'm sure we'll hear much more about that. So just a little background on Sera before I invite her up. She received a PhD in theoretical astrophysics in the year 2000 at the University of Arizona, and held a couple of postdoctoral fellowships, one in Europe at the Max Planck Institute for Radio Astronomy in Germany, and a second one at MIT in the United States. She joined the faculty of the University of Amsterdam in 2006 and became a full professor of theoretical high-energy astrophysics in 2017. She's an expert in the study of compact astronomical objects such as black holes, and she develops complex observations and works on the modelling and interpretation of their signals. She provides scientific leadership of the Event Horizon Telescope collaboration, and in 2016 she was a founding member of this collaboration, and also served as a member of its scientific council as vice chair, and currently sits on their scientific board. Sera has received a number of prestigious prizes for her work, both collectively as part of groups and also individually, and I'll give you some examples of those. As a member of the Event Horizon Telescope collaboration, she shared major prizes in 2021 for producing the first images of a black hole, and including the Breakthrough Prize for Experimental Physics, the Einstein Medal of the Albert Einstein Society, and the Bruno Rossi Prize of the American Astronomical Society. And individually, she's received many more honours, and just a few key examples. She's a fellow of the American Physical Society and an elected member of the Royal Netherlands Academy of Arts and Sciences, and the Willem de Graaf Prize for Public Outreach. I'm sure that I've embarrassed Sera enough, and so with that, I'd like to invite you up to give the 2024 STAG Lecture. Thank you.
All right, thank you so much for the kind introduction and the invitation to be here from the STAG committee and being part of this prestigious lecture series. It's really nice to be back in Southampton. For those of you who don't know, Southampton is a sister city of Amsterdam, not in the way you would usually think, but for black holes. In fact, we have a lot of overlap in our research directions, and there's been quite a lot of trading back and forth of faculty and students and researchers. So I used to come here quite often. It's been about 12 years, I think, since I'm here, but it's nice to be back. And I just want to also thank all of you for choosing to come out in such force on a Wednesday afternoon to, hear about black holes for an hour. And I hope I can do it some justice. So I thought that I would start maybe with a bit of audience participation, just really quickly. I mean, Phil sort of ruined it for me because he pointed out these have been on a lot of newspapers. But I guess my first question would be, just show of hands, how many of you have seen not just one of these images, but both of these images before today? Okay, that's actually pretty good because a lot of people tuned out. It's never possible to be as exciting as the first one for the second one. And then my other question would be a little bit harder, which is how many of you have a sense of what it is we're actually looking at here? You are experts, okay? I don't need to give this talk. No, we'll see how far it goes. But what I wanted to kind of bring this up is because on the one hand, these are these sort of fuzzy donuts, and I'll be talking quite a little bit about this, but it doesn't look exactly what's been shown to us in the media, like when you think of something like Interstellar, right? And why does it look so different? And so what I wanted to do is start by talking about these images. That's kind of the focus of my talk, but I'm going to meander through history, a little bit of background. There should be something for everyone here before I come back and put these into context. Okay, so Before I say anything, I just want to say, okay, these are the two, groundbreaking images of supermassive black holes. Now, these it's kind of amazing, right, that you could do this. And what you're looking at is not the black holes per se, but you're looking at the light being emitted just outside the event horizon of these two objects. And so what I'd like to do is kind of say a couple words about the EHT. First of all, this is a huge group of about 400 international scientists. And so I want to make clear, as Phil said, collaboration in science is very important. I am representing the team. There are many young people in this team. And in fact, even some secondary school students help us with our analysis. So some of you in the audience, if you're excited by this, it's not that far away for you, okay? Let's get to it, and let me tell you a little bit about them. So I'm going to introduce the cast of characters here. Now, on your right, you have M87 star. We use this asterisk to say we're looking at a black hole, which is in the center of the M87 galaxy, which is relatively nearby by our standards, which is 55 million light years away. And the star is to say that we're talking about the black hole rather than the galaxy itself. Now, this is one of the largest black holes that we know of. It's 6.5 billion times the mass of the sun. And we measure the physical size of a black hole by the size of its event horizon. And that scales directly with the mass. So when we say it's a really huge black hole, both in mass and in size, to give you some idea, the entire event horizon of this black hole could eat our solar system out to Pluto. So it is a very big black hole. Now, in contrast, Sagittarius A star, this is actually the black hole in the center of our own galaxy, the Milky Way. You'd think it should be called the Milky Way star, but for historical reasons, because it was discovered and it looks like it's in the Sagittarius constellation, that's where it gets its name. So we say Sag A star. And it's not a very exciting black hole by black hole standards. It's about 4 million times the mass of our sun, which is pretty small. So it's about 1,500 times smaller, but it's 1,500 times closer. So that's why these two black holes look very similar to each other on the sky. Now, there's a couple things I want to say about this. I mean, first of all, they look like fuzzy donuts, right? And if you were thinking about really amazing astronomical images that we're used to from Hubble telescope or James Webb, you might not be really that impressed. And I'd like to try to, over the next hour, give you some sense of what's lying behind these images. They were very hard to get, first of all. And what's inside there is really the convolution of strong gravity. So, and I'll talk a little bit more about what that means, and really interesting astrophysical things that we'd like to understand about, what happens to stuff when it gets really close to a black hole. But in order to understand either, we have to separate these two effects. And that's very difficult, especially when you have only something quite fuzzy. So I will be talking quite a bit about that. Another thing to keep in mind is that these are the only two black holes that we can do this for right now in the universe. And that doesn't mean that these are the only two black holes in the universe. There's billions of black holes, but it's a bit of the Goldilocks problem, as we say, that you basically can only see as good as how, the smaller you can see or the more distant you can see depends on how big your telescope is. So our planet has a fixed size. If we use that as the max telescope we can build at the moment, that sort of tells us what size black holes we can see. And then also how sensitive our telescope is tells us how bright objects we can see. And so these happen to be the only two right now that fit the bill for our particular planet and telescope. But that doesn't mean we can't see many more if we make some changes and improvements. So I'll talk about that as well. And I think it's also just important to note that most of what you've seen so far has come out of our 2017 campaign. So when we first started observing, but we have tons and tons of data coming. We've been looking every year for the last years since then, except for during the pandemic. And so we're starting to publish it. It took a long time because it's very difficult, but we're sort of moving out of the everything the first time mode into a little bit more of production mode with some of our analysis. So you can expect to see quite a bit. And by the end of my talk, I hope I can give you a little bit of a taste of that. Okay, so what have we learned, from these? And I'm going to give you the big reveal of what we think was something pretty important. Memes. So when I was lucky enough to be part of the team that got to present the first images in the press conference in the US. And, we're nerdy scientists. We didn't really think anyone would pay that much attention to this. And so we were pretty bowled over by how much this traction this had on social media. And it really made me start to think, why is this? And I think part of it is that you think black holes are scary. People find black holes pretty terrifying. So by memifying it, it makes them a little friendlier. It gives you a little bit more, association with these. And plus, it is a pretty good analog. And from everything from cat's eyes to the other side of the cat is also in here. And funny story is that we actually presented some of these at the Royal Academy in the Netherlands, and that was probably the first time they'd ever seen Snoop Dogg there, so that was also fun. But we, took this to mean that there was a certain resonance with the image, and there's been a lot of thinking about this also in the fields of history and philosophy of science, why this is so important. I sort of started to think myself about this, and it reminded me that, this resonates also with something else that maybe reminds us in some way of something else, which is pretty scary. So this is my second main audience participation, which is just shout it out. What would you say is the most scary astronomical thing that you can see with your eyes in the sky? Are they scary? I mean, stars can be, but especially when they die and become black holes, right? But what about something that you could experience maybe once in your lifetime, if you're lucky, where maybe the sky changes quite dramatically? Total eclipse. So in 2024, last year, we were in Mexico for our EHT collaboration meeting. And this was a photo of the total eclipse in Mazatlan. And you notice that this image is kind of reminiscent, right, of what we see. It's not an accident. In a way, it's a good analog because, we just happen to have this, blocking of the light, in this case by, the moon blocking the sun for a while. But in the case of what we're looking at, a black hole is not blocking the light, and it's not necessarily in front of the light, but it's absorbing the light via its event horizon. However, it is somewhat reminiscent, and I think that maybe something about this kind of ancestral terror around the eclipse creeps into our image as well, because throughout history, people have been pretty scared by eclipses. We know this is a pretty mundane event now, but you can imagine that when you had no idea what was happening, the sky goes dark. All across the world, we have records of how people saw this. I mean, I was reading actually that an eclipse was associated with the death of Henry I, so it happened also here in England in the 1100s. But when we were in Mexico, I was also thinking about local traditions. And so Mesoamericans have a very rich astronomy history. And this was some of the documented versions of their eclipses in their history. And what you can see is that they generally associated with war or, catastrophes. But my personal favorite is the fact that they had an idea that the sun was basically fighting its way every night through demons and sort of monsters out there that were eating suns. And I think they might have been onto something. So an eclipse is also an interesting point of view because, in fact, there are monsters out there, which we call black holes, and they do eat suns. And so that was kind of my segue into the field a little bit. This is what's called an X-ray binary. This is the small stellar, there's two kinds of black holes, the supermassive ones that we look at with EHT. This is another type, which is called the stellar mass black hole. Stars form preferentially in binaries. And what happens, and this is an artist's impression, so it's a very pretty movie. We can't see this exactly with our telescopes. We know what's going on. And when one star is very, very massive and goes supernova, then it leaves behind a black hole at the end of its life. And if it still stays in this binary, it eats its companion star. And over time can, really change the future evolution. We also know supermassive black holes can eat suns as well. I brought this up as well because I just want to mention that one of our colleagues here in Sotan, Professor Pojak Gandhi, this was actually a movie made for a press release from a paper that we collaborated on, focusing on these. And the other reason this is interesting is because people, firstly, this is the first kind of black hole that we discovered, actually, and thought was a candidate black hole, this small type. And I'll come back to that in the history part. But we also get asked all the time, how is it that you can see a black hole? And you saw, right, that there's this kind of halo around what we call the shadow, similar to the eclipse. That means that there has to be light that's emitting outside the black hole. And that light is emitted through structures like this. So we call this a disk. Basically, it's not always disky, but you have a bunch of matter spiraling in. And then near the black hole, you often launch these extremely fast, near the speed of light, magnetized flows, which we call jets. And the light that we see around the black holes comes from something like this. So from the astrophysics point of view, this is extremely important science. I'll explain why. And we want to be able to understand it, but we have to pick apart the gravity effects, as well as understanding where they contribute. So for the rest of my talk, that was kind of the intro in to get you in the mood, but now I'm going to talk a little more about the history, and then I'm going to talk about what we know now about black holes. And part of the reason I'll start with that is that by the time I get to the Event Horizon Telescope, this will make a lot more sense to you. So then I'll get to the EHT and its results, and then at the end, I'll say a little bit more about where we're going with the field now and what we're starting to learn. Okay, so we have to start with gravity. I'm sure you all know what gravity is, but it's an interesting point of view that going from this, what we call the Newtonian model of gravity, towards the more relativistic Einstein version. One way to think of it is that in this Newtonian view of forces, so forces are something that we experience in our everyday lives. We're most familiar, probably besides gravity, with the electromagnetic force. It's something that operates on a property of the object. So the electromagnetic force operates on something that could be like charges. And that means that you're familiar with this. If you try to take a kitchen magnet and stick it on a teacup, unless that teacup's made of metal, it doesn't stick. So it doesn't care about the mass, but it cares about the electrical charge. And so when Newton first started formulating, gravity, and people thought of this as a force, everyone thought of it as quite a similar thing. It was a force that operates on objects using, something that has mass, and it didn't care about their charge, for instance. And what Einstein did a little bit over 100 years ago, so keep in mind, this is an extremely new science compared to many other sciences. We've only been able to understand black holes conceptually for about 100 years. But he said, nope, this is not right. In fact, we live in a four-dimensional universe. There's, the dimensions of space, but there's also time. There's this weird fabric called space-time, where these four dimensions are all working together. And mass is not something that a force is acting on, but in fact, mass is creating a warp in this space-time, which mimics a force. And it sounds nuts. And actually, at the time that he was saying this, a lot of people did think he was nuts in the beginning. And so it took a while for people to start to get their minds around this. And I think some of you did some of these experiments earlier in the morning, but one way we try to give people some intuition for this is we build somewhat inadequate 3D models or 2D models to try to explain this, but you can get your sense about what this means by putting like something heavy in a piece of rubber. And the idea, of course, that if you flick a marble across a flat sheet of paper, it will go in a straight line because it has to follow a straight path if nothing deflects it. But now if you warp the fabric, then that marble will also follow a warped path. And that's very similar to what happens to light also embedded in space-time. What's interesting, though, is it also depends how much energy that object has. So if you give a marble enough energy, so here's first the marble coming, it has so much energy, it escapes. But if you don't kick it with enough energy, it sort of gets trapped. Now, this has nothing really to do with gravity. I mean, it's an analog, but it's an important point that you can actually stay out of a gravitational potential if you have enough energy to orbit. And this is really helpful in case you get close to a black hole, because you will not fall into the black hole immediately if you can orbit it. And it's the same thing. Our planets are orbiting the sun. We haven't fallen in a long time. So angular momentum is really important in this. But it also means that photons actually can go around a black hole many times and escape if they have just enough energy. And that's something I'll be coming back to. But we often make also these kind of figures to explain this deep potential well. And the idea is that every object that has mass is bending space-time. So you and I are bending space-time, but very, very little. It's not detectable. But if you have, like, the sun is bending space-time, compact objects that are on their way to being a black hole, like white dwarfs and neutron stars, bend space-time. And then black holes bend space-time so much that you can also think one way to imagine what the event horizon is that it's the region where light doesn't have the escape velocity to get out. That basically the escape velocity, which I think some of you also learned in the masterclass this morning, if the escape velocity itself is light or faster than the speed of light, then light can't escape. So that's one way to think about what's happening in the event horizon. Another way I like to think about it, it's not exactly mathematically correct, but it's kind of a nice analog, is space-time really isn't static. It's almost more like a fluid. And so you can think about space-time itself being dragged towards the black hole. And when you get to the event horizon, space-time is actually moving towards it at the speed of light. With the spinning black hole, can actually move with the speed of light around the black hole and drag light and everything else with it. So it's pretty profound. Now, these ideas, like I said, were kind of crazy, or thought they were crazy at the time. But there's obvious consequences. And one of them is that the sun should bend space-time around it. And so if you look at the sky before and after, when the sun passes over the background stars, those stars should change positions a bit if Einstein's theory was correct. So this was a big thing that people did right after World War I, when there was a little more attention to things like this. Einstein and his friend Lord Eddington decided to test this out with, again, the solar eclipse. So this is why I also think solar eclipse is a nice kind of segue into this. And so they went to different places. Eddington, they went to a little island off the west coast of Africa called Principe. And this is the actual photographic plate that they took. It's been cleaned up with AI apparently, but it's nice. You can see the labels, of course, were not there. But you can see the sun is very active when this was happening. So there's a big coronal mass ejection. But these stars were the ones whose positions were measured, and it fit this theory of general relativity. So this was kind of the beginning of this transition. And the thing that made me really laugh, though, is it didn't it didn't catch on immediately, certainly among physicists. But this was in the New York Times soon afterwards. It was on page 17, not super high up on the list. And similarly important as 2 franc dinners in France, and maybe the Dutch giving up the Kaiser. But it says, men of science more or less agog over the results. Stars not where they seemed or were calculated to be, but don't worry. And then at the end, they just some funny things basically saying, so far, his attempts to explain this haven't been very successful. So people were not really sure where to believe in this, but things did change quite rapidly, and in his lifetime, he became extremely famous quite soon after, because this really changed the whole paradigm. And some of you have seen Oppenheimer, and you know him from the nuclear bomb. Well, nuclear bombs have a lot to do with astrophysical objects, and so there's a lot of crosstalk between them, and he did a lot of astrophysics as well. And so it was really this paper in the 30s where he and Snyder showed that you could have a real astrophysical object collapse and basically go into its own event horizon smoothly without breaking any sort of laws of physics. Now, before that, people had thought that this was a nice theory, beautiful, mathematical, worked out, but they didn't really believe that something like this could exist. And it was papers like this that started to turn the tide. However, nobody had discovered one of these before, and they thought, okay, we'll just call it a gravitationally completely collapsed star. That's a very hard thing to say all the time. So eventually they got to name black holes, but there's a funny story that I'm not going to tell because it's even more of a shaggy dog story. If you want to hear it, you can ask me in the break. So how did we actually start to discover, once this theory was there that these could exist, how did we get to actually seeing black holes? And for that, I need to start talking a little bit about observations. I think many of you are familiar with the electromagnetic spectrum. Light exists over many, many frequencies more than our eye can see. And what's important is that our atmosphere doesn't let all of that through. That's good for us because some of these wavelengths, like X-rays, would not be good for humans and life on Earth. So the atmosphere blocks it. So this image shows where the color hits the ground. Those are bands that actually make it to the ground. And where it doesn't, you usually have to go to space. So what happened was, up through most of human history, we only had our eyes and the visible. We could see that from the ground. But then after World War II, there was radar, radio detection and ranging was perfected, and radio astronomy became a real thing. So from the ground, we suddenly had a new wavelength. And then slowly but surely, people started to map out, going up into space with the space race. And that played a really big role actually in the discovery. So X-rays in particular. And I just want to mention that sort of in this in-between area, this is the frequency that we're looking with the Event Horizon Telescope. It's the highest frequency in the radio band, and it's kind of getting up towards the infrared. And the atmosphere does get in your way, especially with water vapor. So you want to be in high and dry places, which limits the places on the Earth that we can build our telescopes. And I'll come back to that. So space race happened. Laika and the Sputniks came up, and it made the US panic. And they created NASA during the Space Act. And then in the 60s, people started sending up rockets into space, and they were looking for X-rays from the sun. Particularly, they thought the sun would be a bright X-ray source, which it is, and be bounced off the moon. And they didn't really expect anything else. But instead, they found a bunch of extremely bright X-ray sources, one of which turned out to be Cygnus X1, which is this type of black hole that I was talking about, where it's a black hole that's about 21 times the mass of our sun, eating its companion star. And, the question was, did people believe this right away? It took some time. There was different types of ways that you could kind of confirm this. The X-ray properties seemed to be what we expected theoretically from a black hole. And then many people by the 70s basically accepted that this was a black hole because what they could do is they could look with a telescope, look at one star in the optical, which was visible, moving around an empty spot in space, basically, and they could measure the wobble and just use essentially Newton's laws to tell you what kind of mass had to be there, an invisible mass. But it raises an interesting question of what do you need really to prove that you're seeing a black hole? Stephen Hawking didn't believe it. He was one of the last holdouts. This was actually from one of the science museums. And he liked making bets. I don't know if you've heard stories about this, but he often made bets with his friends. He and Kip Thorne had a bet. And Stephen Hawking came out already in 1974 saying, no, I don't think it's a black hole, even after most people in the astronomy community accepted that it was a black hole. He finally ceded the bet in 1990, well after I think most people kind of got on the bandwagon about this, but it's kind of an interesting story. And you may have heard, I know that Roger was speaking in the same series some years ago, but there was a Nobel Prize a few years ago for the theoretical framework for black holes. But interestingly, they don't talk about a black hole here. They are very cautious. Andrea Ghez and Reinhard Genzel, using two different telescopes, one in Hawaii, one in Chile, measure the motions of individual stars. So our telescopes are that good now that you're looking at individual stars moving around. That's where the black hole is, in the center of our galaxy. And it's using these motions that we could weigh the black hole and say there's a 4 million mass black hole or some object is there. But they were quite cautious. They said a supermassive compact object. They didn't say a black hole. So what do you need to see a black hole? And I think a lot of people think seeing some direct evidence of the event horizon. And that was kind of one of the motivations behind what we were doing, is trying to get that additional data point as well as testing general relativity. So I'm going to take another segue, and I'm going to say a little bit more about the role of black holes, what we've learned about them since, before I get to the EHT. And part of the reason is because you need to understand what it is we knew when we were starting to design our telescope, and how did we think that we could actually start to take these measurements, and we had to design our telescope in the right way to look for the right thing. And that required a lot of the knowledge that we've learned in the intervening time. But I think it's also interesting for you. Many people think that black holes are just these kind of boring objects. I mean, they're kind of weird and scary, but they don't do much other than just suck up everything around them. And I want to kind of change your view on that. They're very important players in the universe. So people often are afraid when they hear that there's a supermassive black hole in the center of the galaxy. There's a sense that it's going to suck us all in, right? But as I was saying, firstly, if you're orbiting, it won't. But actually, the reach of how far away a black hole can typically grab material and start to even pull it into orbit and put it into a gravitational bound system with it is actually quite small. So this is an analog to our galaxy. We can't zoom out like this, but it looks very similar to this. And Sagittarius stars, reach of what it can capture and bind to itself is about 100,000 times bigger than its event horizon. Now that sounds pretty big, but when you put that on a scale of the galaxy itself, it's barely a dot in here, and the galaxy is another 500,000 times bigger than this. So what that means is that from the point of view of being outside that reach, where we are, or even near that reach, the black hole doesn't affect you at all when the black hole is in a very dormant state, like the black hole in our galaxy. But one of the things that we started to learn as we looked at many, many galaxies and many black holes, this is a beautiful image of, there's something like thousands of galaxies in this tiny piece of the sky about the size of a grain of sand from JWST. Each one of these galaxies has a black hole in the center. And what we're finding is, don't worry about this mathy thing, but just this is basically the black hole mass plotted against a proxy for the mass of the galaxy. And you see that there's over orders of magnitude, there's basically a pretty tight correlation. And what this is telling us is that black holes seem to, in some ways, grow together. At least, well, there's a lot of questions now about this, about the early universe since JWST, but at least in a general sense, we think that there's some talking between the black hole and the outer galaxy. But if the outer galaxy can't feel the black hole because it's too far from its reach, how do they talk? How does the black hole tell the galaxy, I've grown or something's going to happen, you've got to adjust. And the way that it happens is when the black hole becomes active. And I want to show you what that looks like. So this is a cluster of galaxies. It's the largest bound structure of objects in the universe. These are not stars. Each one of these is a galaxy. So it's kind of like the birthing ground of galaxies. And we're looking at this with the optical, like it's basically with Hubble. So it's what you would see if your eyes were really good. Now, there's a big galaxy here with a big supermassive black hole in the center. All of these have black holes, but this one is in an active state, an especially active state. So we're going to switch to other wavelengths that we can see outside what our eyes can see, which are the radio and X-ray. These are very important wavelengths for black holes in general, as I kind of said before. If we look at this, blue is radio, so we're translating it into a color that you can see because you can't see with your eyes, and pink is X-rays. These are the jets that I was telling you that the black hole launched. So the single black hole has launched a jet. These are 800,000 light years, or about 1 billion times bigger than its event horizon. It's actually much bigger than the galaxy itself. And so you can see there's no problem for the black hole to talk to the outer reaches when it's in this active state and it's launching these really big jets. This pink stuff is basically gas that is on the order of the temperature of our solar corona. So it's like 1 million degrees, extremely hot, but space is almost zero, right? So what happens is all this energy from the black hole, from the interactions, is basically stored in this gas. And you can see that the jets come out and they sort of expand and form these bubbles, and they're dumping. We can measure basically the energy being dumped there by how big the bubbles get blown up. And we find that it's on the order of like 100 billion supernova. So one black hole can basically, put an enormous amount of energy into its environment. And this can change the growth of galaxies around it. It can actually stop stars from growing. So this is a very important process for us, and we try to understand this in cosmology. But if we want to understand how this works, we need to know what's going on near the event horizon, because that's where all the action is happening, where all this extreme gravitational energy, that's the source, it's the power and the fuel, gets converted into these other forms somehow. There's another reason we're interested in these jets, and this is more in my field, is that these are big magnetic synchrotrons. So very similar to like CERN or the LHC, they use magnetic fields to accelerate particles. We think that these are the sources of the highest energy particles that we see on Earth. They can excite particles up to like 1 million times more than what we can achieve on Earth. So it's also a particle physics lab for us. And we're starting to be able to directly detect not just light, but particles, and we call this messengers. So in my title, I talked about multi-messenger. I won't say too much about this, but it's important to remember that not only are we looking at these objects in light, we're starting to be able to detect, these are particles called neutrinos. These are gamma rays. It's basically light at very high energy that acts like a particle because it's so high energy. But we're also starting to see, as we heard also in the prizes, that there's these things called gravitational waves that come from mergers. And since 2015, we're living in a whole new era where we can actually see the ripples in space-time. And this is another way that we can see black holes. So we call this the multi-messenger approach, that we're trying to look at black holes from all these different angles, and each one tells us something different or unique about the theory, and then we can try to put this all together. So, so that's kind of the background. And I hope that that gives you, it's a very fast review, but now I'm going to start talking about the Event Horizon telescope and where this idea came from. So I'm first going to show a movie to help you understand the image, and I'll keep coming back to this. This is a movie that we made. Here's a black hole. Imagine that this is our camera or our telescope somewhere very far away at like infinity. And we're going to be doing some ray tracing. This is quite similar to what happens in games. If any of you are gamers, we basically actually even use GPUs to do a lot of our calculations, and we're tracking what happens to light in space-time that's warped. Now, you're not going to see the disk and the jet around this black hole, but imagine that there is this astrophysical structure around it that's emitting the light, and now we're just going to trace what happens to it. We like to decompose, it's kind of useful, into what we call n's. We basically say 0 it's how many times a photon or a particle of light will make a U-turn around the black hole. So n equals 0 means the light is mostly coming from behind the black hole, coming to our camera, and you see that it gets deflected. This is exactly like the marble with the ball, because space-time is bent, but it expands, and this is something called gravitational lensing, which I think you also learned a bit about if you were in the master class this morning. But that image is mostly showing you about this astrophysical stuff. But now, if you go to basically a full U-turn around the black hole, you can see that the light can come from any direction, also in front of the black hole. It wraps around and it focuses the light into a very tight ring. And then each time you add another U-turn around the black hole due to space-time effects, you're focusing closer and closer to the sort of critical last orbit and beyond which the photon would fall into the black hole and not escape. But in principle, photons can go around many, many times. And what we're interested in is separating out basically this ring feature. We call it unoriginally the photon ring. Scientists always use these kind of unoriginal names. So there's two elements hidden in that fuzzy image that we see. There's the ring. This is tracing the shape of space-time. It can tell us if general relativity is correct because there's very clear predictions for this. The shape and deformation can also tell us about maybe there's alternative theories or can tell us about the spin of the black hole. But in general, Einstein's general relativity predicts that this ring should be on the order of about 5 times bigger than the event horizon itself due to this expansion. So what we're trying to do when we measure this ring, we're not looking actually, this shadow here is not the event horizon. That comes from some of these light projection effects. And it's sort of an imprint of it, but it can also be change its shape due to the astrophysical light. We're really after this photon ring, and we're trying to pick out this part. Now, to do this for the black holes that we're talking about, we need to have a telescope that could basically see, like the head of a pin or read a newspaper in New York City from here, which sounds pretty crazy. So you can calculate how big a telescope would have to be, and it turns out that for the frequencies we're using, it needs to be about the size of the Earth. So yeah, that sounds a bit bad. And in fact, people talked, you can't exactly build a telescope like this. It would be gravitationally unstable, not good real estate for the people underneath it. If you had a planet to spare, you might think about it. It would also be very expensive. Funding agencies don't like that. So the idea is that we basically did a cheat, which is called interferometry. This is a well-known technique where you build telescopes across the Earth, but in this case, we don't have that many because it was a new wavelength and we needed these high and dry regions to do this. So it's a relatively sparse array. And then actually I'm going to skip over this and I'm just going to go to I'll talk a little bit about it. But what you're doing in effect is by having this array, you're sampling the pattern of light on the sky. And if you wanted a lot of sensitivity, the more dishes you have, the more collecting area you have, the more faint an object you can look at. We only have a handful of telescopes. So that's why we are limited to fairly nearby and bright sources. And then the biggest baseline tells you the smallest thing on the sky you can see, and that's the size of our Earth. So this is, as I mentioned, the EHT collaboration. We had a long period of having to meet online during the pandemic. It was we do a lot of our work online because we're spread across the entire globe. There's a lot of painful 2 a.m., 3 a.m. telecons for me and everybody else. But we also meet in person about once a year. And then we do a lot of work in smaller teams. And so the telescope itself wasn't our own. We actually borrowed telescopes from other people who are run by other facilities, and we string them together in a mode where we can do these observations once a year. We're given this time. And we're not even given the time. That's actually the wrong thing to say. If you know anything about how astronomy works, we have to apply for time on these telescopes. So we're competing with other people. So we write competitive proposals, and we get about 6 to 7 nights within a 2-week period once a year at the moment. In the beginning, in 2017, we had 8 facilities. Then in 2018, we added the Greenland telescope all the way up north. And then since then, the array has been expanding in both in France and in Korea. We've added, and this is a whole array. So the sensitivity has gone up. And this is just to let you know that the data that we're getting from this period is going to be much better than what I'm going to be showing you, but we're not finished analyzing it yet. In 2024, we added another set of telescopes as well. And also, we're using a shorter wavelength, which means we get a little bit like maybe 5%-ish gain on the sensitivity or the precision as well. But that's where we are at the moment. And then basically, one of the things that I do as well in the collaboration is I try to coordinate what's happening here with this with telescopes on the ground and in space so that we can get all this complementary information that we need, because we need to track the whole system, not just the ring, and we're trying to put it all together. So what was the main result? If you think about testing general relativity, then the size of the photon ring is the first and kind of obvious test. And so you could say, well, we know the mass of the black hole, we know its distance, we know that the mass tells us the size of the event horizon, so then it should be 5 times bigger. And then basically, you can just line things up and say, oh, that's pretty good, you know, it works, general relativity is correct. But of course, that's not at all how we do things in these studies. We have to do very sophisticated modeling, and that's actually where I'm the most busy. So I'll just give you a little hint of that without going into too many details. What we do is we build black holes in a computer. Usually we're using supercomputers and high performance computing. We set up a black hole in the center. We wrap, this is a sort of slice through a 3D donut. So we sort of seed it with material. The black lines show you magnetic fields. We let it run, and this is kind of showing you a top down. So this is that disk. And what you're going to see is that over time, very quickly, you start to get ordered fields, and this is the jets. And the jets get launched to very large distances. And here you can see the magnetic fields being wrapped up, and basically you end up with this disk jet kind of system. And then within that, we have to make some models of how the light is created and make fake images that we compare to our actual images. And you can see this looks nothing, right? You're probably thinking to yourself, what is this? This looks nothing like the images that you just showed me. So I want to explain a really important point. And I'm going to use another simulation for this. So here you have the disk. And you notice, by the way, that this isn't a very thin disk like what I showed you or what you saw in Interstellar. In the kinds of black holes that we're looking at, the disk is more like a tornado. And that has to do with what's called the state of the black hole. And I won't say too much more about that, but so you have this big tornado of stuff, and then you have the jets being launched. And this is what it would look like if we looked at it with lower frequency radio. So the frequency that we observe at can pierce through all of this, and we want to get down to the event horizon. So we chose the highest frequency we can go, almost like the X-rays of radio, to get through all this stuff. Otherwise, you're looking at the surface of a cloud. So what we're doing is we're sort of stripping away all of this information about the astrophysics, and we're getting down to what, and this is in our models, you know, what this looks like at its base. And then we compare these to our images and we try to see, you know, are we on track or not? And then eventually, by using multi-wavelength and other facilities, we try to then build it back and understand the connection of this region to all these other structures that we're seeing. And this is also a big test of our models. And I'll give you some examples of this. But this is kind of a run-of-the-mill simulation and what it looks like after we've done what we call general relativistic ray tracing. If you had no blurring and the perfect planet-sized telescope that I showed you, which isn't possible, you would see something like this. This is sort of, you have the ring, the photon ring, which is the prediction of general relativity, and then everything's kind of moving and swirling around the black hole. So you have this fluff from the astrophysics, and we're trying to pick these things apart. But when we blur to show you what it looks like with our very not so good telescope, but it's the best we can do at the moment, it's a fuzzy donut. And how do you tell, you know, how do you pick out the part that isn't moving from the part that is moving? And this means this is space-time effects versus astrophysical effects. You can see what the problem is. Now, if we had movies like this, it would be a very easy problem for a machine learning approach. You know, you could just put, you know, artificial intelligence on it and say, find the part of the image that isn't moving and the part that is. And it's very good at picking things apart like this. But remember, we're only looking once a year. And I'll talk about what that means, but that means we are basically getting a snapshot at the moment. And so that makes it very difficult for us to do this kind of decomposition. So what we do instead, you know, we run many simulations. So it's a really computational intensive thing. And then each one of these simulations has, you know, thousands of snapshots. And in our first papers, we had a pretty limited set of just, you know, 50 or so models with 60,000 snapshots that we were comparing. And of course, we've been building on this library ever since. But the thing is, our limit on how good we can test general relativity is because what happens is, and this is just to give you an example, some of our models, this has a weak magnetic field or a strong magnetic field. Some of them have different black hole spins or orientation. So we're kind of changing parameters that are both associated with the space-time and the black hole, or changing stuff in this geometry around it. And the ring size, remember, tells you how big the black hole is. So this is a smaller black hole with like more astrophysical fluff on the outside. This is a bigger black hole with more astrophysical fluff coming on the inside. It's not inside the event horizon. These are projection effects because the light gets bent. And you can see the same here. And these are really different models, but they all look the same when you compare it to our image. So we have a problem picking apart pretty fundamental theories. And that's the limit on testing general relativity for us at the moment until we can do a better job. So I want to that's kind of where we left off with our first set of papers. And what I want to do for the rest of my talk is talk a little bit more about where we're going with this. And one of the things to point out is that the differences in this astrophysical fluff is that it's a mix of this geometry of the jets and the disks, but it's also very dependent on this particle acceleration. And that's where the multi-messenger comes in, and that's something that is personally pretty interesting to me. So for the rest of my talk, I'm going to just give you a sense of what's happening in the event horizon, as we say, and hopefully you'll come away now with a better sense of what's in these images, but also where the field is going, because it touches on many other fields. Okay, so at the moment, we not only have the two images that you've seen, but we've taken what's called polarization. What this really means is that we're able to, these striations are not the actual detection. It's a way of us kind of representing the data in an artistic way. So think of it as Van Gogh a little bit. But it shows you the orientation of the polarization vector, which gives you information about what the magnetic fields are doing. And the magnetic fields are a really big parameter. That's one of the things that tells us how these big jets are launched. So it's very important for us to understand what the magnetic fields are doing. And we have this now for both M87 and for Sagittarius A star. And so this is very constraining for our models. And I'll give you an example of that for Sag A star in a second. But by doing all this modeling, we're starting to rule out different parts of parameter space, particularly for the astrophysics. So the GR, as I said, we're managing to say, yes, we're consistent with general relativity within about 10 to 20%, 10% for Sag A star, 20% for M87. To do better than that, we need to start getting movies, so we need to have more information. But for the astrophysics, what's very interesting is that these black holes basically seem to be very similar down at their base. So both the fact that the images look similar just tells you, of course, that we've used the right filter, the right wavelength to get down to basically the event horizon that we're seeing. But they're embedded in very different systems. So M87 galaxy is a big elliptical, and it's in this active state where it's got this huge jet that is punching through its galaxy, and it's interacting with its galaxy. So this is that active state I was talking about. Sagittarius A star, if you zoom all the way in, these are sort of spirals of gas coming in. We don't see a jet at all, but our theories would tell us that with the same, they seem to have very similar kinds of magnetic fields near the base. We think that it should have a jet. So this is a really big, question for us at the moment. What's happening down near the black hole? And are the magnetic fields actually the same? And then why is there no jet like this in our galaxy? Or is there a jet and we're just not finding it? Or are our theories wrong? So this is a very active region, place at the moment in our science that we're trying to understand this. And I'll give you a sense of what we're trying to do to figure this out. And one way we do this is we start to combine more information. And as I said, sort of bring out all the large scale structure. So this was from the campaign in 2017. And I'll just go through a couple of the horizons of what is coming and what we're working on at the moment. This paper actually came out a couple of years ago, but we're really only taking the first baby steps in terms of incorporating all of this into a model. So I showed you that sort of image. This is from the Hubble telescope. So you see the galaxy. Here's the jet. We took all of these exactly at the same time that we took this iconic image. So we have information going from the radio, which gives you, depending on the telescope you use and the frequency, we're building back that jet and getting information about the larger scales. And then we're also piercing through with the X-rays and gamma rays. Gamma rays have terrible resolution, so the whole system just looks like a dot to us, but we can get information about the flux, and we've got X-ray that shows the entire jet. And we're trying to figure out, what's going on with this at the moment. And And so here's, again, that simulation. So one of the things we need to start doing is, up until now, we've made models that had to fit this image. Now we need to make our models fit all of this. And that is very, very difficult. And that's where we're going to learn a lot about fundamental things like particle acceleration and plasma physics and things that are probably well beyond what I would talk about here. But just to give you a taste of where this is and how fundamental it is. Now, STAG-STAR, I'll give you an idea of how important this is, because we did begin this process. We had some more time between M87 and STAG-STAR, and we improved our models. But one thing that's amazing is STAG-STAR is flickering constantly across the electromagnetic spectrum. So this is showing you our observations in the radio. This is a model, but I'll just say, we're starting to think that there might be some kind of orbital motion near the black hole. There's several reasons for this that might be driving this kind of flickering. And in the near infrared and in the X-rays, it's basically popping on and off. And what we're looking at is something very similar to solar flares. We think that this is like magnetic reconnection in this kind of, hurricane of stuff. And so if you've ever seen movies of the sun's surface, imagine this happening right outside a black hole, and that's what we're trying to understand. So we're taking this information now, and we're trying to actually put this, so we started now you remember I said we had 50 of these kind of models. We actually have about 400, but we used 200 that we called our kind of conservative set for STAG-STAR. Oh, let me go back because I didn't want that movie to start right away. And what we do is we start to use these constraints of the images itself, using all this data from all the wavelengths. So the size gets rid of some of these models, but not too many, because we kind of knew the size already from GR. But as we start to put in the shape and the orientation, multi-wavelength, which means the data from radio to X-ray, we're running out of models. And finally, we got down to kind of 2 best bet models out of all the ones. By the way, this is a really inefficient process computationally. We have to find a better way to do this. But adding the polarization got rid of one of them. So if you believe this, we've managed to kind of find, maybe this isn't the exact model, but it's one of the models in a part of parameter space that's telling us we're really starting to home in on what's going on near this black hole, and this will help us improve our test of general relativity. Another horizon is going from snapshots to movies. So little black holes are smaller, and so they change faster. The time scales for stuff to move around a black hole scales with its size. So basically, Sagittarius A star is 1,500 times smaller, which means this is kind of a clock sped up, but it takes roughly on the order of like tens of minutes for stuff to go around the black hole. If you look closely, this is changing very slowly, but for M87, it's on the order of weeks to months. So if you think about it, what's happening is we have 2 problems. When we look for a couple days once a year, we're seeing one snapshot of whatever M87 is doing. But with STAG-STAR, it's way too long, and our data isn't good enough to see all this. We have to integrate all this out, so we lose information about the dynamics. So the 2 things we need to do is look more often so that we can start to see the motion in the slow one, and we need to improve our telescopes so that we can start to break up this, smearing into its actual component parts. So we're already starting to do this from 2017 to 2018. This is new as of this year. The ring shifted by 30 degrees. This is very interesting. We're not sure what it means. There's a lot of different theories. Some of this could be related to fundamentals around the black hole, but it may have to do with the fact that the jets are actually moving around as well. So we have plans now for 2026 campaign to actually look for maybe like 10 or something times within a couple months. We're trying to, we have to discuss this with the people who own the telescopes, right, to be able to work this out. But hopefully we're going to be able to start to get more data points into this movie. And so one of the key points here is that we're also trying to expand the array. And this is something else that I'm involved in. So yellow shows you the dishes that we had already. And then basically in white, green were the ones added in the last couple of years. And then in white, you're seeing proposed dishes, and the more that we can cover the plane of the Earth, the better. And you see there's a huge gap in Africa. So we lose a lot of information. We're trying to integrate, the Earth is turning as we're collecting data. And when this part of the Earth is looking up at the black hole, right now we only have these 2 telescopes. So we don't get a lot of information until the Earth turns enough to start getting all of this. When we can get a Canary Islands and Namibian telescope, that really helps fill in the gap. And so that's actually something that I'm involved in. Rob Fender's at Oxford. This is a big grant from Europe as well. And we're working very closely with the University of Namibia. And in fact, these are the first 2 ever astronomy PhD students in Namibia. So we're helping also working with the department to build up astronomy at the same time so that this can be a sustainable project. And I just want to mention that we do a lot of outreach in Namibia. We have a dome that goes across Namibia to remote schools. It's run entirely by astronomy students. You can see our image there. And these students, Shigrid, Delight, and Hiko, who was, sorry, oh, I missed it. Well, that was Hiko and Lot. They actually got to go to the big Royal Astronomical Society meeting this year, and they won a big award for outreach here in the UK. So I just think it's really important to mention that. Okay, so the idea is that as we have this new dish in Africa, we can start to go, here's a fake model, but we can start to basically go from something kind of garbagey, which we get at the moment, to a really nice ring. And that's going to help us make these kinds of movies. And so we think that we'll be able to start to resolve. This is like a fake image that we're testing our software on with the array. And we're saying we think we can resolve if there's some kind of motion that's driving this flickering. Another thing is in 2018, we looked again at many of these jets, but we also saw this is a gamma ray flare. So it's basically a bunch of particles being excited at the exact moment to very high energy in the jets, we think, that we looked at the event horizon of this black hole of M87. So one of the big questions at the moment is how do we model this particle physics now, this multi-messenger approach at the same time? And that's something else maybe if you're interested, you can ask me about. But it's a signature of extreme particle acceleration. And we likely think that these events are also associated with neutrinos. So ever since 2018, these big jets have been associated with particle events coming from very high energy things like neutrinos and gamma rays. And most of the bright spots in the sky that are starting to add up are in fact the big jets from black holes. And finally, there's all the small black holes I was mentioning, and the sky is constantly flickering. And these are called transient events where the black holes are going on and off. They turn on and off. Also, the big ones do over millions of years, but the small ones do this in human lifetimes. And so when we expand the Event Horizon Telescope, the Africa Millimeter Telescope, which is the one in Namibia that I'm involved in, but other ones as well, will help monitor these. And then we're going to have enough power to basically start to look more often and basically make direct images of these smaller jets as well. So the idea is to also start moving away from supermassive black holes and start to explore smaller black holes and other interesting objects as well. I'm almost done. This is my last sort of content slide. If we want to do any better than this, we have to go to space because we're limited by the size of our planet. If we want to see these rings in other distant black holes, we have to make a larger baseline. So there's 2 projects being discussed at the moment. They're still just concepts. One is based in the US, one in Europe. One, the Black Hole Explorer versus the Event Horizon Imager. And the idea is that you just put telescopes in space. So I'll just show you kind of what this looks like. This is a representation of how good your telescope is. And so basically, the more you fill this white space, the better it is. And you have 3 telescopes in orbit that start spreading out, and they basically start to flesh out. You know, you can see there's the key is you want to have as many different distances between the bases, but it doesn't use telescopes on Earth. Everything is done in space. Another design, which is the Black Hole Explorer, has an element in space and is connecting to our ground array. And then it starts to, this is what M87 would see, and this is Sagittarius Star, but it's much, much better than what we have now. But it's expensive. You know, space is expensive. So these are things that we'd like to do, but it takes time and money, lots and lots of money. So if you think this is cool, tell your government to help us build things in space. And that's really, I've come to the end. So that was a whirlwind. I hope that this gave you a much better sense of, you know, what's in our images more than just the project and the rings itself. Really, we have lived in a special time. It's been 1 century roughly since Einstein even came up with the basic ideas that would allow us to understand black holes, and we're now directly observing them. And I would just say it's really cool that we can see black holes, but EHT is definitely setting a new benchmark for this. Black holes are not passive. They play a really important role in the universe. I hope that gave you a little bit of a sense of why we're interested in studying them and why the event horizon region is so important for us. We need to figure out how these jets and things are launched and what's happening down in that region. But they're also much better than LHC for studying particle acceleration at high energy, and that's something else that's very important for us. There's lots of other cool things I didn't tell you about, so if you have other questions, and I understand there'll be some time even after the questions to hang out at the poster session, you can ask me. And it's expanding. So this is the beginning of a large-scale project where we're looking at putting more telescopes on the ground in space so that we can actually eventually get to the point of testing things like general relativity much better, but also the astrophysics. So thanks for your attention.
Thank you very much for this fascinating talk. We have time for questions. Please wait, raise your hand.
And don't be shy. There's no dumb question, really. Actually, the dumb ones are the hardest ones. Usually, they're usually not dumb.
Yes, you said that the photon rings were within 10 to 17% of general relativity's prediction.
10 to 20.
10 to 20. So assuming that's not an issue with the telescope's uncertainty, what would be the explanation for why those photon rings are significantly are larger than predicted?
Oh, they're not larger. It's just that we can't constrain. We can say that they're the right size they should be, plus or minus about 10%. And that really has to do with the fact that we're trying to pull apart the size from this fluffy ring. And it's because of our forward modeling and our uncertainties about the astrophysics. So it's just basically the decomposition is uncertain. So that uncertainty in our actual theory of the astrophysics, this is common actually when you're trying to get to general relativity or dark matter or fundamental things. Astrophysics is often a difficult thing you have to remove to get to the, so, for me, it's the important thing, but for theoretical physicists, that's the pesky bit. So if we can better constrain the astrophysics by all these things I was talking about, the idea is that you will be able to constrain this ring to the point of actually making a very strong test of general relativity. And that's why we need to go to space, basically, to do that. Does that help?
Thank you.
Okay.
Yeah. Hi. It's probably a dumb question. I probably missed something obvious. The fuzzy donut, why isn't it symmetric?
So it's a good question. Actually, it's interesting because in Interstellar, I don't know, did you ever see Interstellar?
I did, yeah.
One of my big grouses about Interstellar is that they didn't include what we call Doppler beaming. So so there's two things going on. When you say symmetric, do you mean the light pattern or do you mean the?
Yeah, so there's obviously a hotspot.
So if you're familiar with the Doppler shifting, this is the same effect as like when you're listening to a train, and it comes and it sort of, as it gets closer to you, the pitch goes up and then it goes away, the pitch goes down. What happens is when light, you have the black hole is spinning and all this stuff is basically being dragged along with it together with the black hole. And what happens is it's moving towards us, like in the case of M87, faster with relativistic effects that amplify this. So that stuff is moving towards us at the bottom and kind of away from us at the top. And so what's happening is it's the same effect, Doppler shifting, but it's in a relativistic framework. And it has to do, we think, with the dragging of light around the black hole. I mean, it's an interesting point because we also have to think about the fact that the black hole can drag stuff around it and spin in the opposite direction of the stuff that's moving around it as well. So we think, though, that we've now managed to actually pin down the direction of the black hole spin at the same time.
Hi.
Oh, there you are.
When you're imaging the black hole, are there other sources of noise in the frequencies that you're looking at, and how do you deal with those?
Okay, so I mean, there's different kinds of noise. One of the noise that's pretty common are things like radio frequency interference or something. But the fact that we're in these very high, dry, and very remote areas, that tends not to be the biggest problem. The biggest, in a way, what you want to think. I mean, there's obviously noise. Any instrument has noise, and so that's dealt with just like any other instrument. You try to model, you try to characterize it as well, and that goes into our error analysis. One of the biggest uncertainties, again, besides some of our theoretical part, but what contributes to the sparsity and some of these fluctuations are the fact that we're trying to link, these telescopes, and we're not doing the linking in real time, and we have sparse data. So what happens is you basically take the data and you have to put it on disk, it's petabytes, and then you use like atomic clocks to mark every wavelength to know when it was taken so that it can be in a supercomputer put all together. Then when you model to reconstruct the image, what you have to do is add certain techniques to kind of fill in the gaps. And so basically, that's one of the main causes of our image uncertainty. And the fuzziness comes from that sparsity, as well as some of the uncertainties and our reconstructions and modeling. So there's many things that contribute to this, but at the moment, the only way to get like a perfectly sharp image would, of course, be to have an Earth-sized telescope or to fill in all those gaps. Yeah.
Yeah, it was a really, really good talk. Thank you. Over here.
Where are you?
You mentioned these jets. So that's emitting some form of electromagnetic radiation. Why are they forming that jet shape exactly? Is that the magnetic fields of the black hole? And exactly what is making those jets up?
Yeah, that's a great question. We're all really wondering this ourselves. This is kind of what we work on. We try to do the modeling. I mean, what we think is happening is that the magnetic fields play a pretty big role, but also the external environment kind of has pressure. And so you have extremely fast stuff being pushed out and channeled by the magnetic field. So everything is basically charged. So it feels the electromagnetic forces, and the magnetic fields can kind of channel this together with the fact that the disk has a lot of pressure and kind of keeps everything into a channel. But when things are moving faster forward than they are expanding, of course, they can kind of keep a sort of shape like that. If you think about like a garden hose, right? I mean, if you crank up the power, you can keep a pretty sharp, line of water fire hoses can go for a long way. So it has a lot to do with also how much power and thrust, and the fact that these jets are extremely linear out to billions of times bigger than the black hole suggests that they're just insanely powerful as well. But we actually don't really understand how they don't start to, twist and fall apart at some point. So the magnetic fields probably play a role there as well in kind of stabilizing things.
Thank you.
Yeah. This one.
Thank you very much for your very exciting talk. My question about parameters, you mentioned that we are run out of parameter models. And my question is, what are actually parameters of your model, and how many of them?
Oh, I mean, it depends on who you're talking to, because I mean, when you're reconstructing the radio images, there's a lot of parameters that go into the kind of analysis of the uncertainties in the reconstruction of the sparse image. And this can be done in different ways. Some of this is almost like using AI and Bayesian techniques.
It's more like empirical parameters rather than
so in
GR.
empirical parameters, if you're thinking about it, you have basically the black hole mass, which tells you the size of the ring you're putting in. You have the orientation and the configuration and strength of the magnetic fields, and you have the disk. It's all your initial conditions, basically. So you set things up kind of as a guess of what things are like. There's a lot, I can't go into these details, I think, in a room like this, but if you're interested, I can tell you. But so you start with disk properties, you start with magnetic field properties, then also the orientation of the magnetic field, the spin, and the disk, the spin of the black hole. Those are your basic parameters.
Thank you.
Yeah. And the particle physics, which is a big question mark.
You say that the next stage, and to really get the data you want, you need to go into space.
Where am I looking? I saw the mic over there. Sorry, say that again.
Strikes me there's two practical problems. One is radio telescopes need to be a lot larger than optical ones. How are you going to achieve that? And also, how are you going to get your petabytes of data back?
Yeah, these are great questions. So this is something that's been a really hot topic. So radio, the dishes actually don't need to be that big. Like the ones that we're using in EHT, they can be on the ground on the order of 12, 15 meters. Obviously, if you go to space, you'd like to go bigger than that. There's some really interesting technology at the moment where people are trying to do like inflatable or expandable or, things like that. So you might be able to get a bigger dish out there. Now, the downlink is something that has really bothered people for a long time, but with the space industry at the moment, there's been a lot of work, and you're getting up to the point of hundreds of gigabits, I think, per second downlink. You might be able to get around this, of course, if you had one of the options is not to have anything going down to the ground, but actually do all the correlation and everything in space, and maybe use the moon. So there's a lot of different ideas, but I think the idea of getting fast downlink of your data, it's not to the point of petabytes per second, but it's moving in that direction. And I think this is something the space industry wants as well. So we're working together, hopefully, to kind of piggyback on those developments. Yeah.
Hi. I was wondering, you mentioned that the spin of the black hole is kind of proportional to the size, right?
Oh,
so,
no, not
or inversely proportional, or
the ring size is proportional to the mass of the black hole. The spin can be quite random.
Yeah. So have you tried modeling zero spin?
Yes. Yeah, we have. So one of the things that's interesting is that there does seem to be a correlation between the spin of the black hole and the power in these outflows, the power in these jets. And so when I was sort of hinting at the puzzle between the two black holes, one of the things that had been proposed for a long time was that M87 would have a very high spin, which would help. Basically, you can tap the spin energy. Actually, it's a Penrose process. You all maybe were at Roger Penrose's talk, but he's somebody who helped develop this theory that you can tap the spin energy of the black hole and help power these jets. So people have thought that if you have high spin, you'll get powerful jets, and ergo, M87 has high spin. Then you would also say as a corollary that Sagittarius A star must have low spin because it doesn't seem to have powerful jets. But as far as we can tell, it looks like we're favoring a pretty high spin from all of our other kinds of modeling. And so either something's missing or wrong in our theory, as I said, that we're not piecing things together correctly, or it means probably there's something else different between them that we haven't quite figured out and we have to learn, and that's probably in the particle physics. Does that explain what you're asking?
Yeah, thank you.
Okay. Where are the ladies in the house? I want a question from them. Good.
Hey, why can't we already observe these black holes like multiple times a year?
Because we don't own these telescopes. That's actually one of the advantages of building our own. So the ones that were the first wave of these telescopes were all existing facilities. And that's part of the reason that we could go from concept to design and to actually running the project within a very short amount of time. Because we didn't have to build the telescopes ourselves. We just had to kind of make them talk to each other. But the problem with that is that when you're borrowing someone's car, you can only use it when they want you to use it. So we basically have to negotiate. And these are very high demand telescopes that are used by the astronomy community, and people use them, especially our core is called ALMA. It's a very powerful telescope. It's an array itself in Chile, and it's extremely popular and very hard to get time on. So we sort of need that as a big anchor station and some of these other bigger ones, and they have agreed as a team to work together with us, but they're only willing to do it for about this 2-week period. And then within that 2-week period, we're given about a week. If we can, this movie campaign would allow us at least once to be able to try to do more observations within 1 year, but that's very difficult. You also have to know, I didn't talk much about this, but we don't know which nights we're going to observe. The reason we get a window is that there can be bad weather or problems across the array. And so every night we have a stressful discussion. Well, are we going to trigger? Are we not? And so, you're wasting telescope time on the nights that you don't trigger. And so it's a bit difficult. And if we actually own our own telescopes, we would have a lot more control over this. So what we're hoping is to start moving into a way of being able to actually operate where we can even use mostly our own telescopes and occasionally borrow the ones from other people, but it gives us more flexibility. But the simple answer is just, the fact that these belong to people and they use them. Oops, not on.
Thank you for the talk. Do you have the charge of the black hole as a parameter for your models?
Yeah, the charge of the black hole. Yeah, so it's interesting, right? I mean, this is an important concept in theoretical physics, but for astrophysical black holes, the charge of the black hole we think is generally shorted out, because you're basically surrounded by a plasma. And so charge doesn't become important for us. It would just be, vanish, even if it started with the charge. There are some in our modeling, like if you want to look into the details, there have been people who have tested things like the kinds of metrics that involve charge as well. We've also done things like test wormholes, many other kind of alternative theories. But at the moment, I think we're not at the point we can really test that level of things. I don't think charge will ever be an important one for us, though. Yeah.
Thank you.
It's a very interesting talk. I'm just going to ask, non-technical, is there any spin-off technologies that came out of this that could be used for your public?
Yeah, that's interesting. Probably yes. There's a lot of crosstalk between our techniques. And in fact, some of the things that we're trying to develop is also going into like the space, industry as well. That's not really my area of expertise so much. I mean, in the larger sense, not so much this particular project, but in the larger sense, things that you probably use like Wi-Fi came out of radio astronomy and, these kinds of techniques. And in fact, actually, maybe I should show, I had a slide on this. It's actually kind of interesting that let's see, whoops, no, I don't want to. That was the story about the, sorry. I'm afraid if I go, I wanted to show you one thing. Okay, here, let's see if I'm still sharing the screen. So maybe you didn't know this, but another spin-off is actually when you're using GPS, you're using black holes. So the entire navigation system is calibrated using telescopes like the one I'm talking about, but at a different frequency. And this is called very long baseline interferometry, and they're across the Earth. And these are all the black holes in the centers of galaxies that are bright. They don't move, and so they're used to reference, basically. So when next time you look at Google Maps, think about that. But so things like Wi-Fi and internet and so on came out of a lot of these scientific approaches. But I mean, specifically for EHT, I'm actually not aware yet, but these things often take time, so this is a pretty new project. I think just generally driving things into really data intensive types of approaches is something where we're going to be discussing a lot with industry because everybody's on the same boat of trying to get data rates and analysis to go faster.
Excuse me. How does the telescope work? Like the instrument you use to measure to see the black hole, how does it work?
So, I mean, that's a very difficult question, but the sort of simplest answer I can give is that what you're looking at, in a sense, is you're not detecting light like the way that you have, with optical telescopes, you would have mirrors that collect light and sort of bounce it into some kind of camera or detector. With radio telescopes, you're more like almost listening to the light. Radio waves are a kind of light, but they're coming you collect them into what we call a receiver, and you're basically you're actually measuring, in a sense, a temperature. It's very kind of complicated, and then you have to like turn that into basically an amplitude of light. So radio astronomy, to me, is actually, I think, one of the hardest types of astronomy to really explain, because it's a very, very technical kind of thing. But I hope that kind of helps give you an idea. It's basically a radio antenna, and you're converting this into an image.
Second question. In the future, Elon Musk is planning to put a lot of satellites in space.
Can you speak
right?
a little louder? I'm sorry, can I?
Elon Musk is planning to put satellites into space, lots of them, yeah. If they could do basically what you just said, we could use them to watch space even better, and we have a very good resolution because they're gonna be a lot. So,
you mean if we had telescopes on many other planets?
No, on this like orbiting on the surface of Earth, yeah.
Yeah, I mean, the more telescopes that you have, and the further away they are, and the bigger they are, these will help us basically do much more than we're able to do now. So we already do have quite a few telescopes in space, but As I was saying, it really is just expensive, but I think you're right. Like, as we look at the future of humanity, as we start to probably colonize, other planets, I would hope, and move into space. I'm a huge sci-fi fan, if you haven't figured that out. Then, our ability to also study the universe is going to be a lot bigger as well. And I think that's a great note to end on, actually. Thanks for that question. So, and I'm here, so if you have other questions, please ask me afterwards. But yeah, thank you.
Final thing, let you in on a
oh my
thing that has become a bit of a tradition for us. And present. And so this will remind you of the occasion, and you'll have some fun.
Oh my gosh, I'll give it to my mother. Thank you. Oh, that's really funny.
So please stay for a little bit. There are refreshments outside, and some of our students have prepared posters that are hanging in the lobby. Please take a look, talk to them. Also, our students should take a look at the signage outside that tells you how to get your ticket refunded.